All right, guys. From the point of view of regulation and control, there are usually sort of two big ideas, big things you really want to do in the simplest possible terms. The first is you either want to increase the flow rate or the concentration or the concentration, or you want to decrease it, right? That's usually the two things you got going on. So metabolic networks and all systems that require either steady state or other types of uh, 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 flow or behavioral control have inherent mechanisms for doing amplification, right? Or attenuation, right? So in our parlance, right, so this increase in flow or concentration would be equivalent to an amplification effect, and a decrease or an attenuation be equivalent from the way we've been thinking about things as like an inhibition, right? And from the point of view of enzymes, the simplest possible way we could imagine doing that, of course, is by just controlling the amount of substrate available, right? So that's fairly straightforward. If you imagine a classical Michaelis-Menten standard enzyme with this hyperbolic response curve, well, you can sort of intuitively see that by controlling the concentration of substrate available, you can move, up and down the, the response curve for how much product is being made, right? So that's the simplest possible way to control the output of a given enzymatic step. The problem is that that response, the sort of available sensitivity of the response of the output, the initial rate here, product produced, and its link to concentration and flow rate, for most enzymes, from the point of view of this big picture of control and regulation, is just not sensitive enough for a standard hyperbolic enzyme, right? So most control enzymes aren't built this way. They're built with many additional, or in some cases, at least one, in many cases, we're going to see several layers of additional response that give them a far more sensitive response to either substrate concentrations or other molecules that allow them to control these two ideas of or properties of concentration and flux, right? One of the first things that you find in thinking about this, control enzymes don't behave this way. A great many of the control enzymes that are essential fall into a category of response that we talked about earlier. They have response curves that frequently do something like this, right? Many, 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 again, I'm not going to say all, I'm not know if I even want to say most, but a very large fraction of the key control enzymes, these metabolic pathways, turn out to be allosteric enzymes, right? Right. That's a common theme for the control enzymes of metabolic pathways, right? So if you think about that, if you have an allosteric enzyme, depending upon how it responds and what it responds to, you can get all kinds of much more sophisticated behavior out of that, right? So if you, again, here's a simple curve for an allosteric enzyme that's showing a positive homotropic response to its substrate. Relatively small changes now in substrate concentration, right, can give you huge changes, right, in the initial rate. Much, much more narrow response in terms of an amplification response to the substrate change and the output of the enzyme, right? So by redesigning the enzyme, so it's not a classical Michaelis-Menten enzyme, but now usually going to be multi-subunit and responding in a positive homotropic way to the substrate, you can build a simple amplifier with respect to the substrate concentration. Small changes in the substrate, significantly bigger changes in output of the enzyme, right? And you can also have this amplifier work in addition to responding to just the substrate concentration to second molecules, right? So if you want some amplification response to some other signal or some other molecule, if this is an allosteric enzyme, by using a positive heterotropic response and pushing, if you remember, right now we're talking about this idea of having this enzyme, like with respect to hemoglobin, right? Pushing between, say, T and R states, right? As we talked about K-type and V-type allosteric enzymes. In this case, right, if you imagine having an effector that pushed my enzyme in that direction, we could then push the response curve with respect to substrate in this direction. It now starts to look a little bit more like a classical Michaelis-Menten enzyme. The curve gets more hyperbolic. But with respect to a given substrate concentration, say right here, look what happens to the rate of the reaction, right? We get this big, big increase in the response at a given substrate concentration. All right, so at the level of just simple enzyme design, going from a simple Michaelis-Menten to an allosteric response using either positive homotropic or positive heterotropic effects, we can build amplifiers into the output of an enzyme in a fairly straightforward way. Okay, how about attenuation? We think about, you don't only need to just turn things up, sometimes you need to turn things down, right? And there are lots of ways in which you can do this, again, at sort of more or less at the level of the enzyme. One of the simplest ways and simplest things you need often in these metabolic networks to do is have a given enzyme respond to the product of its reaction or some other downstream product of the reaction. You need to sense and know and adjust its activity based upon how much stuff is building up as a consequence of its activity. Now, the simplest possible way to do that is to have it respond to that downstream response is to say, well, if the product of my reaction here, right, is chemically similar enough to the substrate, and if I make the Ki of that product low enough, right, what this enzyme can do, or excuse me, what the product can do, if it builds up, if the Ki is low enough and it's similar enough to the substrate, it can bind to the enzyme and basically block more production of the product, right? This is classical, as the way we talked about it before, product inhibition, but now used in a different way, making the pathway or the enzyme respond to how much of the product it's producing and therefore downstream need in a direct way, right? And so if you remember our discussion about product inhibition, or excuse me, competitive inhibition, what this is going to do, of course, is going to decrease the Km for the substrate without affecting the Vmax. That's important here in a second. And at a given substrate concentration, at a given substrate concentration with a certain amount of product being made, what that's of course going to do is drop the activity of the enzyme, right? It's going to decrease, right? And we have the shift in this curve as the Km. Oh, stop. Oh, geez. As the Km of that curve shifts over, right, we then get a concomitant drop in the output of the enzyme, and we've decreased or attenuated the output, right? Okay. Like I said, that's just classical competitive inhibition, but again, now used to make the enzyme respond to how much of its product is building up, right? Now, there are a couple of problems with this. It's not a universal solution for a couple of reasons. The first is if you look at this curve here, if your enzyme can only respond this way, and if you have more and more and more substrate coming in, you're going to, as we would expect for a competitive inhibitor, you're going to overwhelm it, right? So an increase in the substrate concentration can overwhelm that response, and the enzyme just ramps right back up to the activity you had before. Sometimes that's what you want the enzyme to do in an attenuation response like this. Sometimes that's a serious problem. That's not what you want, right? That breaks your inhibition, or it breaks your regulatory scheme if the enzyme can just be, if the inhibition can just be overwhelmed by more substrate. The second problem is you don't always have a product that's similar enough to your substrate that can work as an effective inhibitor, a competitive inhibitor. So of course, the solution to this is to not use competitive inhibition, but to use something more like non-competitive or mixed inhibition, where the product of the reaction, right, now binds to a second site on the enzyme and acts like a classical non-competitive or mixed inhibitor, where you now, rather than shift the Km, have in classical, of course, non-competitive, no real effect on the Km, but now you attenuate the reaction by collapsing the Vmax, right? And this has, again, that advantage of the product that is now giving you this response doesn't have to be chemically identical to or similar to the substrate, and the attenuation can't be overwhelmed by the substrate concentration, right? So the product builds up, no matter how much additional substrate comes in, you can still control the activity of the enzyme by using a non-competitive response like this. Now, again, this is sort of thinking about this from the point of view of a classical sort of hyperbolically dependent Michaelis enzyme. Sometimes this isn't nearly sensitive enough, and you can sort of probably guess where I'm going to go next with this, which is that the next way you would build a system like this to be even more sensitive is to make a product response enzyme, or an enzyme, the control enzyme, be allosteric and respond to that product as a allosteric heterotypic negative regulator, right? So here again, I've shown this curve again. Imagine again this sort of T to R equilibrium between, say, more active and less active, where the more active enzyme is the R state, the T state is the less active. If the product now of this reaction acted as an allosteric effector that bound to the T state of the enzyme, the less active state, what it's going to do, right, it's going to push that response curve in this direction towards the less active form. And now at a given substrate concentration, of course, the initial rate is now going to drop. And of course, you can now, without very much change in substrate concentration, by using this allosteric response to the product, get a very large attenuation in the amount of output from the enzyme. Okay, now a key idea here, the way I've been talking about this, all of these enzymes, either a competitive inhibition or non-competitive inhibition, or even if the response is allosteric, these are all in a general basket of response of the enzyme to a downstream product. And this is, of course, known as feedback inhibition, where the product of the pathway feeds back to the thing that's making it and decreases its activity. So as too much the product builds up, that automatically, if the enzyme's designed, this control enzyme's designed to sense this way, will attenuate its activity until that product concentration drops, right? And then it can go back up again, right? So feedback inhibition or feedback control is a big deal, and it happens all over the place. And so let's think about that now from some specific example point of view. And what we're going to do over the rest of this lecture is I'm going to take some of these ideas, and I'll introduce some more later, and we're going to layer them onto the pathway we've already talked about. And we're going to start with the TCA cycle and kind of go backwards, back up intermediary metabolism. The reason we're going to do this is because the TCA cycle actually has the simplest level of regulation compared to what happens in glycolysis and gluconeogenesis. Regulation of the TCA cycle is really utterly simple. It exists really in only 3 levels. The first is the simplest possible form that I mentioned before, substrate availability. When substrate availability in the form of acetyl-CoA and or oxaloacetate, when those levels drop, flux through the TCA cycle simply downregulates. If there's not enough acetyl-CoA and or oxaloacetate, you can't drive the TCA cycle, and it naturally decreases. And that is a significant control point because of how much regulation happens upstream of this pathway. Those acetyl-CoA and oxaloacetate pools can be controlled pretty substantially by the inputs that set their levels, right? So that's one level. The second level of regulation of the TCA cycle exists at the level of really only 3 enzymes, right? There are only 3 principal control points. Now, technically, the way we talk about TCA cycle, there's a 4th here. That's right up here, pyruvate dehydrogenase. We'll come to that one next time because from the point of view of regulation, this is kind of a bridging point between glycolysis and TCA cycle. And the regulation here is relatively sophisticated. But in the main cycle, there are really only 3 control points. There are 3 enzymes, and they're right at the beginning. Citrate synthase, right? Isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase, right? And in addition to sort of control through substrate availability, these enzymes have there are 2 additional layers of regulation that exist. For 2 of these enzymes, citrate synthase and alpha-ketoglutarate dehydrogenase, simple product inhibition at 2 levels exists, right? Well, I guess it's citrate synthase, it's really sort of 1, right? So product of the citrate synthase reaction is, of course, citrate, and citrate acts as a classic competitive inhibitor. As the citrate levels build up, citrate feeds back into the enzyme, right, and acts as a classic feedback product inhibitor of the CS reaction. The same thing happens with succinyl-CoA with respect to alpha-ketoglutarate dehydrogenase. As succinyl-CoA levels build up, succinyl-CoA feeds back and inhibits as a classic simple product feedback inhibition of the alpha-ketoglutarate dehydrogenase. Now, there's another major product of this pathway, maybe the major product of this pathway, right? It's right there. It's NADH, right? NADH is the sort of big thing, really, in sort of like a small molecule production coming out of this pathway and just flowing out in sort of a torrent. NADH acts both as a feedback inhibitor for two of these enzymes, the two dehydrogenase enzymes, isocitrate dehydrogenase and alpha-ketoglutarate dehydrogenase. This essential product of the enzyme feeds back and inhibits both of these enzymes when the levels of NADH get too high. But at the same time, NADH also acts as a negative allosteric regulator of some isoforms of citrate synthase. So and you remember, it kind of makes some sense, right? This is that committed step. You make citrate, you're kind of committing, you're beginning to commit those carbon equivalents to run through the cycle. And one of the major control point ideas here is you want to try and have your control points as early in a pathway as you can, because that makes life a lot simpler. If you can get the pathway at the beginning and at the end, you don't have to regulate as much in the middle. And that's kind of what's going on here. So by having NADH act as an allosteric regulator of CS, as well as a product inhibitor of the next two dehydrogenase steps, you get a lot of really good, very sensitive product-based control on the committed steps right at the beginning of the TCA cycle. And just for some additional, and this plugs into additional metabolic needs going on in the cell. If your ATP levels start to build up, some isoforms of isocitrate dehydrogenase also actually are product inhibited by ATP, right? And there's an allosteric feedback from ATP levels that will, from some isoforms, downregulate isocitrate dehydrogenase. Okay, so the next video, we're going to look at the next level up of sort of amplification, attenuation control, gets somewhat more sophisticated, and then see how that begins to impact our next step in intermediary metabolism, sort of in a regulatory way, the pyruvate dehydrogenase reaction.